Hi everyone, my name is Vishal Bakshi, and in this video I'm going to go through Chapter 6 in the Fast AI textbook. And this chapter is about other computer vision problems. Um, Part of going through this chapter involves reviewing Chapter 4 and 5, and the further research section of the chapter also includes some review of chapters, I think, 1 and 2, well, mainly Chapter 2. So this will be a good review of the book so far. This textbook I'm following is part of the Practical Deep Learning for Coders course. Um, Taught by Jeremy Howard, Rachel Thomas, and the textbook is written by Jeremy Howard and Sylvain, I think it's Gugger is his last name. He's a engineer at Hugging Face. And it's a fantastic course. They provide lessons on YouTube through YouTube videos, and then all of the lessons are available in notebook servers as well, including Google Colab. The library is fastai. It's a deep learning library built on top of PyTorch. It's open source, so you can check it out on GitHub. And the community itself has multiple channels. There's a forums.fast.ai. There's a Discord server. And obviously Twitter and YouTube are the most common social media avenues where you can find the community sharing what they're doing. Okay, so I'm just gonna flip over here. And the way I've structured this video is working through this template that I created. So the resources are all in the video description below. I have a Colab notebook where I've worked through all of the code that's already typed in, so you can access that. But in order to kind of create a pseudo live coding experience for the video, I've created this template which has all the explanatory text, has the outputs from the full notebook, but then and also it has comments, but then I've left the rest of the cells blank, so I'll be typing it in during this video. So there's two notebooks that I'm going to go through. One is the overall Chapter 6 overview, which basically steps through the reading and implements the code examples in the reading. You can also find a notebook of this chapter on their website. So you can go here and you can go to Chapter 6. Mine is just a little different in the sense that it's just my walkthrough and has my thought process. So if you want the learning experience, definitely go get the official material. This is more of a learning experience with me that I'm sharing. The second notebook is as part of the further research section. So every chapter in the FastAI text has a further research, which is basically, I take it as the homework for each chapter. And in the further research section, they give you a prompt, either to read something or to implement something. The prompt is actually down here. So the further research section is basically taking what we learned in Chapter 6 about multi-label classification and then applying it to a single label classification problem that we did in Chapter 2. So that's what I'm going to take a look at as well. And there's one piece that I haven't coded yet, so I'll see based on how long this video goes. I may actually just code that live, or if it's going on too long, I might just make a separate video for that. I'll also be posting this on my blog, which is vishalbakshi.github.io. And if you click blog, right now it just has the fast pages template, but I'll eventually, have it up there by the time this video processes and it gets the HD version up on YouTube. I'll have this blog up and running. And then lastly, you can find me on Twitter. My handle is at the Vishal Bakshi. So this is my profile pic. And yeah, I'm trying to get all the channels woken up a bit. Okay, so let's get right into it. So this chapter talks about multi-label classification models, which is basically when you have an image with multiple labels associated with it. So you may have a picture of someone riding a bicycle next to a building, and so you may have a label that says, bicycle, person, building. The second model that we go through is the regression model, and here it's a different class of models than classification. So instead of predicting a label, we're predicting some continuous variable, some numeric quantity within some continuous range. So the very cool thing about this chapter is that we use the same general process for single label classification, multi-label classification, and then finally regression. The only difference is, and it's a big difference, is the loss function that we use and also how we encode the dependent variable, because it's different in each case. So I'm going to start with the setup. This might take a while because sometimes Colab is fast, sometimes it's not. But this is basically how I start every single notebook when I'm working through fastai. So first, I just update fastai because, as I said, it's an open source software actively being released. Updates are being released. So I always run these two lines. So I update fastai, and then I also update fastcore. So this will take a minute. Now that it's updated those two, what I do now is I restart the runtime. So what I'm going to check first is that the runtime is using a GPU, because we are going to train models. And then I restart the runtime so that the installed updates kick into effect. Otherwise, the version of fastai that's installed is, I think, 1.0.61 or something. Okay, so it has restarted. So in this cell, this is mainly just to test. There's no other purpose for importing fastai, but I want to make sure that the version is in fact 2.3. Okay, awesome. And then the last import that we have here is the one that we really need throughout this chapter, which is the vision modules. The hide comment is because of Fast Pages. So in Fast Pages, which is a Jupyter Notebook-based blogging package that's on GitHub, also by fastai, you can put hide in a cell that you don't want presented or displayed in the blog post. So these imports, I'm not going to have those displayed. All right, so I'm going to start here with the data section. So let me go ahead and actually collapse all of my sections and just kind of walk through what those are. So we did the setup. We're going to get the data and take a look at it so we understand what the structure is. Then I'm going to construct a data block, and this is where the first difference between single and multi-label classification reveals itself. And then I'm going to step back and review the MNIST classifier, the 2-digit MNIST classifier from Chapter 4, where we created a model that would be able to classify whether an image was a 3 or a 7 digit. Then I'll look at chapter 5, where we extended that classification from 2 classes to 37 classes, but it was still a single label classification. So I'll review that. And then once I do those two, we'll come back to chapter 6, and I'll look at what the binary cross entropy loss looks like and what the concepts are behind it. I'll take a look at, oops, this should be multi. I'll take a look at multi-label classification accuracy. So the metric that we're going to use is accuracy for multiple labels, and we'll see how that's fundamentally different from a single label accuracy. And then we'll actually train the model and look at the results for the multi-label classification problem. And the last thing I'll do is take a look at the regression model, which again is going to be very similar, but we'll see that the output is very, very different. And the problem it's solving is also very different. Okay, so let's start with the data. So fastai comes with many, many useful built-in functions and objects, 2 of which are the untar data method and the URLs object. So the URLs object has a list of a variety of different freely available data sets, URLs that are I think they host on Amazon S3 or something. And then untar data basically takes those images and downloads them. So I'm going to save that to path. And then once it comes in, I'm going to read it into a data frame. So the path is going to have a CSV for training. So it's going to show file name, what the labels are, space delimited, and whether or not the image is included in the validation set. So that's what we'll take a look at here. All right, so I'm going to run that. So first thing that's going to happen is that it's going to download the data set. So right now it's downloading all the files, including the images for the Pascal data set. Okay, so here we see the same data frame output that we did before. One other function or one other attribute of the path object is ls. And so just like in terminal on command line, when you say ls, it lists the files and directories in the current folder. ls is going to list the files inside of the path. So here there's a test CSV, JSON, train CSV. There's a segmentation folder that we're actually not going to use. There's a training folder with all the training images that we will use, and then train JSON. So in the textbook, they go on a bit of a tangent, but I think it's a necessary one to look at some fundamental data frame attributes and methods in order to access the data. So first, we're going to look at this data frame, and we're going to access all the rows that are in the 0th column. So iloc is a way to get a combination of rows and columns based on their index. So what I'm going to do here is I'm going to say give me all the rows and give me the 0th or first column. So this should give me, as it does here, the file name column. Then I'm going to do the inverse. I'm going to access all the columns for the first row. So again, I'm going to use iloc. And here, I don't have to give it a colon. It just implicitly understands that I want all of the columns if I just give it a row index. So here you can see the first column, or sorry, the first row has column fname as this 005. Labels is just a single label of chair, and this one should be included in the validation set. So I guess I left a spot to do both of these here. So I'm just going to do that with the trailing colon, and then just the row index. I can also access the column by name. So I pass it a string, and then it gives me the same result as before of the full column. And in Jupyter Notebook, you'll see that it has this ellipsis. So it'll show you the first 5 rows, and then it'll show you the last 5 rows, but it won't print out. It's smart enough to not print out all 5,000 rows. I can also do some basic tasks with working on data frames. So I'm going to create a blank data frame object like this. Here's the constructor. I'm going to create a new column. So right now it's a blank data frame. I can add a new column just by referencing it and assigning to it, in this case, a list. And then if I view df1, we'll see that here it automatically indexes using a range index. And then here's the list that it assigned to column A. So I can add another column with some different numbers in the list. And then I can do some operations. So here I'm going to say, take each of the values in column A and add to it each of the values in column B, and then return to me a column or a series object, which has the sum of each element-wise addition. So if I look at the type of object this is, I can see that it's a series object. So each column is a series. Collection of series creates a data frame. Okay, so there's much more you can look into when it comes to pandas. I recommend Python for Data Analysis by Wes McKinney, who's the author of Pandas. And make sure you look at the second edition, which I think was a 2017 release date. Okay, so that's the data, right? So we have a sense of what the data at least looks like in terms of its structure. But we really want to dig in and actually access the data in a way that's going to be useful for the model training purpose. And this is where we get into the fastai API. And the first kind of philosophical difference between other libraries and fastai, which we can see concretely through its API, is this DataBlock. And this DataBlock, I'm not sure how different it is from other libraries, but it certainly is very intuitive and very easy from a beginner standpoint. So it's an object where it just has a lot of helper functions ready, so that when we give it a path of images in this case, or a path associated with any data, the data block knows how to get the independent and dependent variables, how to split between training and validation sets, how to apply any data augmentation to either the items through item transforms or a batch through batch transforms. So it's this very high level data structure, which I think helps as a student, because you have to start thinking about what your data should look like and how your model is going to need to access the data when you're training it. So I'm going to start by just making a empty data block. So we can see here, so right now it's just a data block that's empty. And then I'm going to start giving it some information. So the first thing I'm going to do is I'm going to say, take this data frame and create a data set from it. So what is a data set? So a data set is a collection that returns a tuple of your independent and dependent variable for a single item. So the data set is just a collection of X and Y. And I'm going to give it the data frame, the data set, actually it's plural, the data sets method knows how to handle the data frame object, but it doesn't know how to handle it with the detail at which we need to, which we're going to take a look at right here. So it takes that data frame and it splits that data frame or the rows into training and validation rows. And right now it doesn't know what our structure is. So all it's going to do is it's basically just going to take one row and put it in as the X, the independent variable, and it's going to take the same row and put it in as the Y variable. And then it's going to go on to the next row and do the same thing. But we don't want to do that because that's not going to translate well to what our actual goal is. So our actual goal is we want to take an image, we want to pass it to the model, and we want to output a list of labels, right? And in this case, the list would be motorbike and person. So the input should be an image or something that represents an image, and the output should be multiple labels. So this is where the helper functions or the different parameters of the data block are going to come into play. So the getX parameter is going to access the file name from each row and convert it to a file path. And then that file path is going to be sent to the image block, which is going to take it and convert it to a pillow image object. Okay. Similarly, getY is going to access the labels from each row of the data frame, split them by the delimiter into a list, and then the multi-category block, which is a built-in transform block in fastai, is going to take that list of labels and convert it to a one-hot encoded tensor, which we'll talk about in more detail. The splitter parameter takes a function that instructs the data block on how to split the data set between valid and training sets. In our case, there is a isValid column. So if the isValid column is true, then that image should go into the the validation set. If the isValid column is false, then it should go into the training set. And then it also takes transforms. In this case, we're going to take a random resized crop transform, which does exactly what the name says. It randomly crops the image to whatever size you specify. And we're going to specify one size so that each image in our batch is of the same size. The reason we need to do this is that fastai and PyTorch, when they train the model on your training data, it takes all of those images, splits them into batches, and then stacks all of those images into a tensor, and then applies all of your training steps to that tensor. And in order to apply it, in order to even get it into all into one tensor, every image has to be the same size because one tensor can only have one shape. So I'm going to start defining each of these. So getX is going to take a row of the data frame and it's going to return a file path. Inside of our file path, there's a training folder. And inside that training folder, there's a file with the file name in the fname column. The getY function is going to take the data frame row. It's going to extract the labels column, and then it's going to split it using a space delimiter. So it's going to make a list of individual strings, one string for each of the labels. Then I'm going to take the splitter, which takes the entire data frame, or define the splitter, which takes the entire data frame, and we're going to say that the training data set involves those rows in the data frame for which the column is valid is false. And we're going to convert that to a list. So the tilde character is the not logic. So what we're going to say is if df is valid is true, if df is valid is false, we take the opposite of that, which is true. We take those indexes, convert them to a list. Those are the indexes for training. So in so many words, we're saying that the training data is not the validation data. The validation data is valid, and we're going to convert that to a list. And then it's going to return a tuple with training and valid indexes. All right, so those are the helper functions that we need. I'm going to now create my data block. The transform blocks I'm going to give it are the image block for my independent variable, so the x variable. So that's the first one. And the image block takes a file path and then returns an image object because we want to train on image objects, on the actual pixels. And then for the dependent variable, we're going to give it the multi-category block. And the multi-category block is going to receive the list of labels, and then it's going to convert it into a one-hot encoded tensor. And again, we're going to take a closer look at that in a sec. The splitter parameter just receives the splitter function. The getX parameter receives our getX function. GetY receives getY. And then here, I'm going to transform each item such that it's resized to a square. So I'm going to make it a 128 by 128 pixel image. The minimum scale is going to be 0.35. So what this means is that this data block is going to randomly crop a 128 by 128, it's going to randomly crop at least 35% of the image, and then it's going to resize it to 128 by 128. So this 35% is there just so it doesn't take too small of a crop, such that that crop doesn't adequately represent whatever the image is. So if it's a car, we don't want to just take a small red patch on the door, because then you can't really tell that it's a car. You want to take enough of it so that car-like features are cropped into the training set. Okay, so once I type that out, I can make my data sets again. I can give it the data frame, which we got from the Pascal 2000 URL. I'm going to create my data loaders object. And then I'm going to take a look at what's in our data set. So in the training data set, we should see a tuple where the first value is a image object, which it is here. And the second value is our one-hot encoded tensor. So what does this one-hot encoded tensor show? In this case, it has zeros at every index except for 0, 1, 2, 3, 4, 5, 6. So at the 6th index, it has a 1. So what does this 1 represent? Why is it at the 6th index? So for that, we have to take a look at what's called the vocab of the training data set. So the vocab is a alphabetically ordered list of unique labels in the entire training data set. So here we see that it has aeroplane, bicycle, bird, all the way down to TV monitor. So let's take a look at the image object. So I'm going to take the 0th item in my training data set, which is this tuple, and I'm going to take the 0th item of that tuple, which is this pill image, and then I'm going to call the show method on that image. So here I can see that this is an image of a car. If I look at the second value of that tuple, so again, this is now index 1, I'm going to see my one-hot encoded tensor. So let's look at where this tensor equals 1. Okay, so here where it equals 1 is this 6th index. So I can use the torch where function where I give it this condition, and it'll show me where that which element in that tensor is equal to true. So in this case, I can see that 6 is the index where I had a value of 1. So finally, if we connect that back to our data sets, training, vocab, and then I take this function and I use it as an index, then I'll see that the 6th index in my training vocab is car. So a one-hot encoded list or one-hot encoded sequence is one way to represent, which is one way to index into another different list. Okay. So what we're going to do next is something that they recommend a lot, which is before we get into any sort of training, we should take a look at one of the batches in our data loaders. So let's see. Oh, whoops. Data sets is not correct. So data sets just has the single items. Data loaders then takes that and then batches them into these collections of images. So here I've just shown one row with 3 images, but it looks good. I have images here. This is a car, and the label is right above it. This is a car. This is a motorbike. This shows a bottle as well as a TV monitor. I'm actually not sure where the bottle is inside this image, so that's probably going to create problems. I'm sure the bigger image probably, oh, there it is. You can kind of see the edge of the bottle. All right, so at this point, we have prepared the data such that we can train it using the GPU. So we have a batch ready to send to the GPU and run through the stochastic gradient descent process, calculate the loss function, calculate the accuracy, run through as many epochs as we tell it, and then have a model that we can use for predictions. But what we need to do next is define the loss function. What I'm going to do now is step back, and before we get to the loss function in chapter 6, I'm going to take a look at the loss functions in the previous chapters. So in chapter 4, we made a single label classification model where we wanted to classify 7s and 3s. So there were handwritten digits. Either it was a 7 or it was a 3. And this was a very simple classifier, but its simplicity was very useful because I could really wrap my head around each of the steps, and I could almost manually work through the whole training loop in a way that it would make sense, and it was very intuitive. So the way that we represented the target or the outcome was a 0 was a 7, representing a digit 7, and then a 1 was representing the digit 3. So for example, if we had a batch where we had a 3, a 7, and a 3, the target would be 1, 0, 1. And the question was that how do we take the model's prediction and calculate a loss function such that when it's correctly classifying or predicting what the image represents, the loss function should be low, and when it's incorrectly classifying the image, the loss function output should be high. And so over time, as we take the gradients, it's optimizing towards a lower and lower loss function value. Hopefully, that's our goal. And so they gave an example where, let's say the model output the following predictions for those 3 images in our batch. So let's say the first image, the model outputs a 0.9. The second image, the model outputs a 0.4. And the third image, the model outputs a 0.2. Now a 0 represents 7, and a 1 represents a 3. So if we have 0.9, that's very close to our target of 1. So if we just do 1 minus 0.9, we can say that it was, 0.1 units away from the target. For the second value, that 0.4 was for the digit 7. So how far away was that from 0? We do 0.4 minus 0. The last one is 0.2. So that should have been a 3, but it's closer to a 7. So again, we take the target 1, subtract the prediction 0.2, and then the loss is calculated as 0.8. So we have 2 scenarios. When the target is 1, we take the prediction and we subtract it from 1. When the target was 0, we just take the prediction as is. So 1 minus 0.9 is 0.1, 0.4 minus 0 is 0.4, 1 minus 0.2 is 0.8. And what that does is that when the target is 1 and the prediction is close to it, the loss will be low. When the target is 0 and the prediction is close to it, the loss will be low. And then obviously opposite is that when the target is far away from the prediction, the loss function will be high. So it's the actual teaching, the training takes place in our training loop, but we're setting up a sort of spectrum of true and false in a way that it can correctly learn in which direction it should go in order to minimize the loss. So let's take a look at some code where it just kind of steps through some of that logic. So this is taken directly from chapter 4, where we have an MNIST loss function. We give it our predictions and our targets, and these are both a tensor with all of the batch size. So whatever our batch size is, if we gave it 64 images, then we'll have 64 predictions. If we had 32 images, we'll have 32 predictions. And we're going to use the torch.where method, and we're going to translate the logic that I just kind of went through in plain English up here. So I'm going to say when the target is 1, return 1 minus predictions. Otherwise, return predictions. And then take the average. So if I work through some example here, so let's say I give it this target tensor where the first image should be a 3. The second image should be a 7. Third image should be a 3. I'm going to give it my predictions, which we had above. First image is 0.9. Second image is 0.4. Third image is 0.2. And then I'm going to call my MNIST lost function, give it my predictions, give it my targets, and see what it does. So it takes the difference between each of these. If the target is 1, it returns that difference to 1. If the target is 0, it returns that difference, that distance to 0. And then it takes the average of all three. So if I take 0.1, 0.4, and 0.8, they add up to 1.3. I divide by 3 to take the mean, and my answer is 0.433. And so that's what I get here. So one assumption that is implicit in this example is that our predictions are between 0 and 1. And we need to make sure that the predictions are between 0 and 1 because our entire logic of what is accurate is based on values falling between 0 and 1, corresponding to the target being 0 or 1. So there's one more line of code we need to add in our MNIST loss function. So let me just copy this because all of that will still apply. We're just going to add one more line which says make sure that the predictions fall between 0 and 1. And this is one of the very cool features of tensors as well as NumPy arrays where they can perform element-wise computation if you call some method on the entire collection or entire sequence. So here I'm taking the tensor, I'm calling on it sigmoid, and what it's going to do is it's going to apply, it's going to broadcast is the term, where it takes a function applied to a tensor and then it applies it to each element. So it's going to broadcast the sigmoid function where it takes each one of these input values, passes it through sigmoid, and returns an output value. And sigmoid is a function which takes any number of inputs. They can be, from negative infinity to positive infinity, and it forces them between 0 and 1. Okay, so if I had predictions that were not between 0 and 1, this one line would take care of that so that this logic holds correctly for all scenarios, and I can use that in my training loop. So this was our two-class single label classification loss function. We take the sigmoid of the predictions, we measure the distance from 1 and 0, we take the average, and we return it back as the loss. Okay, chapter 5 takes it a step farther. So in chapter 5, we still want single label predictions, except we used a data set which had 37 different pet breeds. So instead of just handling a 1 and a 0 for each digit, it needs to handle 37 activations for each image. And in order to make sure that only one of those elements or one of those activations is selected as the prediction, we want to make sure that the sum of those activations equals 1.0. So you have 37 activations. You want to make sure that they all sum to 1.0 so that there's always one highest value. Okay? And the reason is, again, this is the purpose of this model. It wants to only classify one label. So we have to make sure that one label is outstanding among 37. So we're going to take a look at that, but similar to sigmoid, the softmax function applies a similar logic as sigmoid, But what it does is that it ensures that not that one element is between 0 and 1, but that the sum of elements equals 1.0. So as a result, each of the elements will be equal to, will fall somewhere between 0 and 1, but the key point is that the entire set of activations, or all the elements in the tensor, are going to equal 1.0. After using softmax to make sure that everything is summing to 1.0, that softmax output is then passed through a logarithm function, so that even further differentiates the highest activation, or the most probable activation, from the rest of them. So we're going to go through and step through that one by one, and I'm going to just give an example here as if we had 4 images in a batch of a pet breeds data set, so that it has 37 activations coming out of the model for every one of those 4 images. I've chosen values from -2 to 2, just to make sure that when I use softmax, it'll give some values that are between 0 and 1, or -2 and 2 initially, and then 0 and 1. Okay, so I'm going to use the torch dot random, and I'm going to say I want 4 rows with 37 columns, and then I'm going to take a look at that. Oh, whoops. I mixed up my English with code. Okay, so this is going to look different. I did not set random seed for the template as well as the full, but the same idea is going to stand. So now I have each one of these rows. So if I take a look at one of these rows, and I look at, well, first let's look at the shape of the entire tensor. So it has 4 rows and 37 columns. Then I take a look at the shape of one of those rows, and you'll see that it has 37 columns. So I'm going to use the broadcasting ability of PyTorch, and I'm going to pass it the softmax function, and I'm going to say that I want to sum to 1.0 across the columns, meaning across dimension equals 1. Dimension equals 0 would be the rows. And then I'm going to take a look at just one row, and I'm going to make sure that the sum of that one row is equal to 1. So, we'll take a look at this in a second. So here's my softmax activation, which is a collection of tensors. Here's the first tensor, and it has 37 values here, and you'll see that after coming out of softmax, they're all between 0 and 1. Here, I wanted to make sure that the sum of this row is 1.0, but it actually says false, and we're going to take a look at why. So if I just do the sum method and call it, don't forget to call it, you'll see that it's a float. And in my conditional, I had just given it an integer. So I need to give it a float, and then it'll say, yeah, that's true. All right, so once I have the softmax activations, they're between 0 and 1, I now want to exaggerate the difference between the highest activation and the rest. So the probability of the highest activation is going to be some value. The probability of the rest of the activations is going to be 1 minus that. So this is where I introduce negative logarithmic loss, or NLL. So I'm going to take -1 times torch.log of the each activation. So again, this is going to broadcast the log logarithm, and this logarithm is has a base of e, the natural number. And it's going to take this logarithm and it's going to take every one of these values, pass it through the logarithm. The reason I need to take -1 is that these values are all going to be negative. So I want to make them all positive. So I'm going to multiply it by -1, the float. And now you'll see here that my values have increased significantly, right? This went from about 3/100ths to about 6. Okay, so that's what? Or sorry, 3/1000ths. So that's about 2,000 times larger. So I'm amplifying these values, but I'm also amplifying the differences between these values. One thing that might help illustrate is what is the maximum value here? What is the maximum, or sorry, what is the minimum value? Let's take a look at those. So the maximum value in this tensor is 0.0925. So that is one of the 37 labels, which is the most probable. That's what the model has determined, that label is the most probable. The one that has the lowest activation, 0.0017, that's the label that the model has determined is the least. And the least doesn't really matter. It just matters that it's one of the ones that isn't the greatest. So I'm going to take that same logic and I'm going to see now what was in the first, for the first image, what was the max and what was the minimum. Okay, so now you'll see that the difference between these two was about 9/100ths, whereas the difference between the max and the minimum is 4. Okay, so almost more than 4 times the difference. So you can see that the purpose of logarithm in this loss function is simply to exaggerate, I shouldn't say exaggerate, but to amplify the difference between the highest probability, which is the highest activation, and then the rest of the pack. What this also means is that it's going to amplify the model's biases. It's also going to, if it thinks that this is a car, it's going to exaggerate that. So this is one of the differences that we're going to see between chapters 5 and 6, is that we, and I guess I shouldn't say amplify its biases. I'm not sure. That sounds right, but I don't know. I haven't read enough on that. But what it does amplify is its prediction. And it amplifies a single prediction. The difference between single label and multi-label classification is that in a single label classification, we want to amplify a single element because that's what we're trying to achieve. In a multi-label classification problem, we don't want to amplify just one. We want to know, if there are multiple values that are pretty high. And that pretty high is what we're going to take a look at in the form of a threshold when we talk about binary cross entropy loss. But let's finish through here and really walk through an example like we did for the chapter 4, so you can see what this looks like. So we're going to continue with this 4 image batch. So we're going to say the first image is going to have the 4th value in the training vocab. The second image is going to have the first value, then the 34th or 35th, and then the index of 10. So these are the targets. The targets for what? The targets for the labels of the 37 pet breeds for each of the images in our 4-image batch. We're going to create a index, which is just a range index from 0 to 3. And then we're going to pass the index IDX for the row, and then we're going to use our targs as an index for the columns. So if you remember up here, we have 37 activations for each row. We want to pull out index 3, 0, 34, and 10 to see what the model predicted for those activations, because they correspond to those labels in the vocab. We have 4 images, so we're just going to pass the index of this tensor, right, 0, 1, 2, 3, as the row. So when the IDX is 0, we're going to pull index equals 3. When the IDX is 1, we're going to pull the 0th activation, and so on. So again, this is going to be different from your full notebook, but the idea is the same. We now have we now have the activations pulled for each one of these. I think that's it for this piece. The last thing I want to do is define the loss function. So I'm going to look at cross entropy. We're going to give it our activations. We're going to give it our targets. The index is going to be the range of the length of targets that we have. The activations we're going to pass through softmax. And then we're going to take -1 times torch log of the activations. Whoops. And then we're going to return the index targs of the NLL loss, and we're going to take the mean. Okay, so what I want to do is I want to compare the function that I came up with and compare that to the built-in functions for cross entropy that fastai and PyTorch come with. So I'm going to do cross_entropy. I'm going to give it my activations, which, let me make sure, okay, it was this ACTS, so it's just my acts. So my activations, and then I'm going to give it my targets. And let's see what that does. All right, cool. So it takes the mean of those here. So I think earlier I mentioned negative logarithmic loss as NLL. That's incorrect. I mean, it is taking the negative of the output of the logarithm, but the NLL stands for negative log likelihood. There's also a couple other points I want to talk about these maximum and minimum values that are very important to understand why this works with the overall theme for SGD, which is we want to minimize the loss in order to get accurate results. So I'm going to do this here, and I'm going to say let's use F cross entropy. This is the built-in method for PyTorch. Let's give it my activations. Let's give it my targets. And by default, the reduction is going to be mean, so it should give me the same answer here. I'm also going to use the module version of this loss function. So the cross entropy loss returns a function. So this is a class, and it returns a function. So I'm going to call that so that it returns a function, and then I'm going to call that function and give it my activations and targets. and I get this result here. Just for the sake of an example, I'm going to reduce or remove this reduction towards the mean, and I'm going to tell it not to do that as well in my functions here. So this goes here, this goes here. So here's the full tensor of the 4 images, and you can see that, oh, so I passed reduction equals none to the function that cross entropy loss returned. That's not the case. What I need to do is I need to pass reduction equals none to this class so that the function it returns is not going to reduce. And that gives me that value here. All right, cool. So this is a great check. I recommend if you're working through this book, always check your user-defined functions with the built-in ones. It's a great way to confirm that you've understood at least the code. Something I want to go back to, I had paused the video and because something felt off, even though everything was technically correct in terms of what we were talking about. A very important detail was missed earlier, and this goes to the core idea that we want to minimize the loss in order to find our accurate prediction, or to create a model which finds the accurate prediction. So if we look at our activations here, the largest activation is going to correspond to the largest probability for prediction. But when we take the logarithm and we take the negative, that's a key component, when we perform these two calculations on our activations, the largest activation is going to become the smallest negative log value. Okay, so if I look at, let's do this. I'm going to say, show me the index for argmax. So argmax is a built-in function in PyTorch where you can call it on a tensor, and it'll return the index at which the maximum value sits in the tensor. So here I have an index of 31. So the last one is 36, 35, 34, 33, 32, 31. So here's the maximum value of 0925, and it sits at index 31. I'm going to do a similar thing here. I'm going to give it argmax, but this time I'm also going to give it argmin. Okay, so if we look at the argmin, that is now 31, and that corresponds to the minimum value of 2.38.03. All right, so maybe doing it just explicitly might be more easier. So if I do torch -1 times -1 times torch log of 0.0925. Oh, so it needs a tensor. So I'm just going to wrap this this float inside of a tensor and then pass it to log. It'll give me this 2.38 value, which is the minimum value here. That's really important, right? Because we are selecting out of this index, this tensor, the index at which we have a certain desired result, desired outcome for the labeling. And the value should be small because this is the loss value. So if our prediction is correct, the value should be small. Obviously, if the prediction is incorrect and the value should be large, but the goal is to move towards smaller and smaller loss values on each step of the training loop until we reach some desired accuracy. So I just wanted to make sure I cover that just for my own understanding, but also if you're watching this, I think it's a key point to make sure you get. So at this point, we can go back to chapter 6 and look at the binary cross entropy loss function because it's going to take some elements from the 2-digit MNIST classifier as well as the 37 breed pet classifier, but it's going to implement them in a way that's very different because we have very different problems that we're trying to solve in between those three models. All right, so the first thing that I'm going to do is I'm going to create the model and take a look at some of the activations. So I do that by calling the CNN learner function. I give it my data loaders, and then I give it an architecture, in this case, the ResNet 18 model. So it downloads that. From the training data loader, I'm going to get one batch. So it's going to give me a bunch of images and a bunch of corresponding one-hot encoded tensors. This line I put in there, it may or may not be necessary. I'm not actually sure the situations where it is or isn't, but I came across an issue where some of the tensors were on the GPU, or the tensors were on GPU from the batch, but then the model wasn't. So I'm just making sure that the model is on the GPU, so that the tensors and the model, both on the GPU, can work together to give me my activations. The way I get activations is by passing a batch of images to learn.model, and this is my output. And the activations are a tensor that have 64 rows, one for each image of the batch, and 20 columns, one for each label in the vocab. Okay, what I'm going to do now is first take a look at the final result of binary cross entropy and then work my way backwards to why that makes sense for a multi-label classification problem. So for binary cross entropy, I think I'll just say BCE. So for BCE, I take inputs, which are my activations, and I take targets, which is the one hot encoded tensor with zeros for labels I don't want and ones for labels that I do want. I pass the inputs through sigmoid and store them back in the inputs variable. And then I return this line of code, which is an average loss. And here the logic is as follows. When my targets equal 1, meaning when I am looking at labels that are the correct labels for this image, I want it to return the negative log value of inputs. So the activations directly, of course, with sigmoid applied to them. When my targets are 0, I want to have negative log of 1 minus inputs with sigmoid applied as the loss value. And then, of course, I'm going to take the mean of everything to get a single loss value that then you can take the derivative on and calculate the gradients on the weights and train your model. So why we're doing this is a bit counterintuitive. So I want to work through that because if you recall, in chapter 4, we actually did the exact opposite. When the targets were 1, we wanted 1 minus the activations. When the target was 0, we wanted the predictions itself, the activations itself. So here, the distance from 1 was what we were trying to get when the target is 1, and the distance from 0 is what we're trying to get. We're still trying to get the same thing, but because we're using negative log, it just flips it. That's the main takeaway. That's the main takeaway, but now we're going to look a little closer. So what I wanted to do was I wanted to plot these activations, and I wanted to use matplotlib in order to do that. And matplotlib takes ND arrays, which are a NumPy data structure. However, my y's, my dependent variables, are these one-hot, or sorry, they're not my one-hot encoded tensors. They're my activations. They are tensors, and those tensors currently live on the GPU. So what I'm going to do is that I'm going to take a tensor for one of the image. I'm going to move it over to the CPU. I'm going to detach it from the graph that's used to calculate gradients, and then I'm going to convert it to a NumPy ND array. I'm going to make a X and Y label, so I want to see the vocab index on the x-axis, and I want to see the activation value on the y-axis. I want to have my x ticks from 0 to 19, and then I want to plot a range of 0 to 19 on the x, my activations on the y. Okay, so here are my activations for one image, right? 20 activations for one image. And if I take a look at this, you can see that the activations range from -5 or 6 to +5 or 6. And sometimes it's negative, sometimes it's positive. So what we're going to do is we're going to go back to this BCE function, and we're going to look at what we do in the first line, which is convert those activations to sigmoid outputs. So that's what I'm going to do here. I'm going to take those activations, I'm going to convert them to sigmoid, and then bring them over into a NumPy array, and then plot them. So let me run this. So now all my activations go from 0 to 1. So I've set the stage for the last line, which is this logic where I'm trying to find inputs and then take the negative log when my target is 1, and then 1 minus inputs and then take the negative log when the target is 0. Okay? So the negative log function, what it does, it pushes the differences between the loss values. So let's take a look at this first condition. So when my target is 1, I'm looking at negative log of my inputs. So let's look at -1 times my inputs, then I'm taking the log. And let's plot that. So the sigmoid activations that were very close to 0 are now much larger than those that were very close to 1. So if we look at these sigmoid activations at index 4, I have a very small sigmoid activation, but now when I pass it through negative log at index 4, I have a very large value. Okay, now let's think about what sigmoid represents, right? It's a value from 0 to 1. And what is our one-hot encoded tensor containing? It's containing zeros or ones. So if my target is 1, index 4 should have a large loss value because if selected, it's actually closer to 0, right? It's not being activated very much. So the model is not seeing that label as very likely to be a label for this image. But if my target is 1, and let's say my vocab index is 4, I want that to be a very large loss, right? Things that are supposed to, if the target is 1 and my values are 0, and if they are selected, they should have a very large loss. So that's why there's this kind of inverse relationship where we're doing a distance from 0, but because it's taken through negative log, it becomes a very large distance, and that's why we use that when our target is 1. So if my target is 1, we can see that this is going to give me a very large loss. So the model is going to learn that, okay, no, that's incorrect. We need to minimize that loss. We need to move away from whatever is going on in our model that's predicting that value. let's look at the flip side of it. What happens when our target is 0? In that case, we want to do 1 minus inputs and then take the negative log. So let's run that here. And okay, if I look at 4 now, if my target is 0, and I do negative log 1 minus inputs, it's even closer to 0. And so the loss is going to be very small. So if that happens to be the target and that index happens to be selected, it's going to have a small loss. The model is going to learn that, okay, I'm doing something right. This index is the correct label for this image. So that's the, maybe it's not counterintuitive to you. It certainly was for me. But then as soon as I realized that negative log flips the relationship where small values become larger when you take negative log, and then small values become smaller when you take negative of 1 minus activations for the negative log of 1 minus activations. Okay. And then let's see. I think that's all I wanted to go through for here. So again, the activations are all over the place. We normalize them between 0 and 1. When our target is 1, the ones that are close to 0 are amplified. When our target is 0, the ones that are close to 0 are minimized. Let's also take a look at examples where the value is close to 1. So if I look at index 3, whatever this label is very close to 1. So when my target is close to 1, I'm going to take negative 1 log of that sigmoid. So if we look at index 3 now, that loss is very small because the target was 1, it was close to 1. So the loss is very small. If my target was 0, if we look at index 3 again, the loss is very large because it was close to 1, my target is 0, that represents an inaccurate prediction. Okay. What I'm going to do next is similar to what I did earlier, and we're going to take a look at the comparison between the BCE function that I created and then the BCE functions that are available in the library. So here's my average loss for this set of activations given these targets. It's 1.1025. I'm going to do f.binary cross entropy with logits. Not sure. I think it's logits. But basically, this is applying that negative log likelihood. I'm going to give it my activations and give it my targets, and I also get the same value. Hooray! And then finally, the NN module, BCE with logits loss. I'm going to call that first to get the function, and then I'm going to pass it the input and targets, and that gives me the correct answer as well. Okay, so I have my loss function. That's ready. When the target is 0, it's ready to handle that. When the target is 1, it's ready to handle that. So now I'm going to look at accuracy. How do we determine whether or not this model got these predictions correct? Okay, so first what I'm going to do is I'm going to look at single label classification and the accuracy we used for that. So this is straight out of the book. We took our predictions. We said which one of the indexes has the maximum prediction. Where does the prediction do the predictions equal the targets, turn that into a float, give me the average. So where it's true, the float's going to convert it to 1. Where it's false, the float is going to convert it to 0. This is single label classification, so it's only going to be true in one spot, at one index, which is why we use an argmax function. Okay, so we just want one single value where we have the maximum activation. If that's where it's true, then that's awesome. We're going to have higher accuracy. If it's false, if that's not where it's the highest, then we're going to have a low accuracy, and that's going to average out across the entire batch. Okay, so the only reason we have a tensor here is that we have these values across multiple images, but we're only looking at one activation per image. That's what we're looking at here, and then we're averaging them across the batch. Now let's contrast that. Let's contrast that to multi-label accuracy. So this is going to be called accuracy multi. It's going to have inputs, it's going to have targets, and then it's going to have a threshold, which we'll talk about. And then it's going to know whether or not we wanted to calculate sigmoid. If we wanted to calculate sigmoid, it's going to take those activations, apply sigmoid to each one of the activations in the tensor, and then it's going to return the following. So it's going to say, where is the input activation higher than the threshold? Is that equal to where the targets are equal to 1? And then let's take the float version of that, and then let's take the mean. Okay, so remember, our input sigmoid normalizes the activations between 0 and 1. So if our threshold is 0.5, it's going to capture true or false for all of these values, because some of them will be above 0.5, some of them will not. The ones that are above 0.5, we're going to get a tensor that says true. For the activation index at which it's less than 0.5, we're going to get a value of false. Okay. Our target, which is a one-hot encoded tensor for the batch, gets converted to a true or false tensor. So ones get converted to true, zeros get converted to false. We equate these two, or we test if these two are equal. And then we get a final Boolean tensor where it's true when it's equal, false when it's not. We take the float of that to get either 1.0 for true or 0.0 for false. And we take the average, and that's our accuracy. So this threshold is subjective, right? Before, we had no threshold. We wanted just a single maximum. But that's because we wanted a single label. Here, we want multiple labels. So we want to see, hey, model, wherever you're pretty confident, return those labels via the activations that you're returning as high activations. So what does pretty confident mean? That's up to you. And we'll take a look at that in a more kind of systematic way. All right, so at last, we can train this model and see how it performs. So here's CNN Learner. I'm going to give it my data loaders. I'm actually going to use ResNet 50. The metrics I'm going to use is going to be the accuracy multi, except instead of passing a threshold of 0.5, I'm going to pass a threshold of 0.2. But I want to, the reason we use partial, the reason we don't just use accuracy multi and then pass it a threshold of 0.5 is that we don't want to pass metrics, the actual accuracy tensor, because we don't have that yet. We don't have the inputs yet. We just want to pass it a function with threshold ready with point 2 so that when it receives those inputs and targets, it could then use point 2 in this conditional and then calculate the accuracy. So key point here is that you use partial when you want to pass a function with a different parameter, a default parameter. And that's what we're doing here. And it's not a fast AI specific thing. This is just a Pythonic way to do it, and I'm sure in other languages as well. I'm going to give it. That's it, actually. That's all I'm going to give it. So I'm going to now fine tune for 3 epochs, starting at a base learning rate of 1e negative 3. And then the layers that are frozen, I'm going to do those for 4 epochs. So why we're using fine tune versus another fitting method, I'm not going to cover that here. That's a separate conversation. I'm not even sure actually why they chose to do that, but that's something I need to review as well. We are back. So, and I'm actually not sure why, but I got a much lower accuracy. Oh, you know what? I think I know why. Because I used the wrong base learning rate. So I used a base learning rate of 1e negative 3, and I got an accuracy of 75%. So I might as well use this as an opportunity to look at the LR find function. So what this is going to do is, actually, sorry, I'm pretty sure it's okay if I just run it as is, but I'm just going to recreate the learner. Okay. So what LR find is going to do, it's actually going to run through and train the model across one epoch, and it's going to increase the learning rate from a very small value to a very large value, and then it's going to plot the losses. Okay, so what I did was I used 1e negative 3, which was around here. So it was not a very steep change in my loss, which probably means that if I would have trained it for a few more epochs, then maybe this would have improved. What they used in the book, I believe, was 3 e neg 3. So here's one, and they used, or sorry, here's one, so somewhere around here, and here's 3. So I guess in this case it looks kind of the same, but I'm going to try it out. Maybe actually, let's not do that. Let me just pick something that's steeper. So I'm going to try. Let's see. It's steepest at 4 e neg 2. So maybe I'll try something a little before that. So maybe I'll try like 3 e neg 2. All right, so I'm going to run this again and stop the video so you don't have to watch the progress bars with me. All right, so my model has run and my model has been trained, and it took about 3.5 minutes to run. So that statement is correct here, but I didn't reach 95%. I only reached about 93%. So that's, that's just how it goes. Hopefully you can reach 95% or higher. So I'm going to take a look at my results, and I'm going to look at 18 images. All right, so here it's going to show what the comparison is between prediction and actual. So here, this one didn't get anything at all. This one had a dog, no prediction here. Bus and a car, but here this only predicted car. Horse person predicted as horse person. Train as train. Person as person. Bicycle and person was accurate. Car, motorbike was actually translated to motorbike and person. So yeah, lots of interesting ones here. I have run this model quite a number of times, and this is sort of the trend I see. It's really good at capturing cars and people, um, but some of the more nuanced ones it didn't catch. But at the same time, I only looked at 18 images, and I think there's like 2,500 in the validation set. Okay, so but at least I can see that it's working, and it's doing the right thing. It's capturing somewhat the essence of what we're training it to do. The last thing I want to look at when it comes to chapter 6 is the last topic they discussed, which was deciding which threshold to use for the accuracy multi-function. So here's what we're going to look at first. I'm going to reset the metrics to an accuracy function that has a threshold of 0.1. And then I'm going to validate, so run it through the validation set, calculate the accuracy, and see what it comes up with. So a threshold of 0.1 basically means that even for small inputs or small activations, the answer is assumed to be correct. So if we look at this function again for multi-label accuracy, input is measured as greater than the threshold. So if the input is greater than 0.1 and it's a correct target, then that'll increase the accuracy. But what we're seeing here is that that actually decreases the accuracy, which kind of makes sense. You might have many different labels activated at a level of 0.1 after it comes back from the sigmoid function. So you may get classifications of labels that are not actually true just because the activation threshold is very low. Let's look at the other end. Let's have a very stingy model where the activation has to be 0.99 for it to consider it a correct classification. So here it falls beneath my 0.2 threshold. So here I only get 92.87% accuracy. So it's not like a higher threshold or a very low threshold is necessarily going to get me the best accuracy. So what value should I use? Okay, that's the main question here. So this is a pretty cool concept that I found very intuitive and very easy to access when they went through this in the chapter. So what we're going to do is we're going to get some activations from the model. I'm going to create this tensor that goes from 0.05 to 0.95, and it's going to have 29 steps. And then I'm going to gather accuracies. So here's my accuracy multi-function. I'm going to give it my predictions. I'm going to give it my targets. And then my threshold, I'm going to vary it. And my sigmoid is going to be false. The reason being that the predictions that I get from getPreds already comes passed through sigmoid. So I'm getting predictions that are the output of the sigmoid function. So I don't want to apply sigmoid again. It's going to mess up the entire range that the entire range that I'm looking at. So we want to say sigmoid equals false. So it's not going to apply sigmoid in my accuracy function. And then I'm going to iterate for every I inside of my input tensor from 0.05 to 0.95. So I'm trying different thresholds from 05 to 95. I'm calculating the accuracy, and I'm collecting them. I'm wrapping them inside of a list. And then we're going to plot it with thresholds on the x-axis, accuracies on the y-axis. And so I'm going to answer the question, which accuracy or which threshold should I use to get the highest accuracy for this model and for this validation set. And here you can see that it's a very smooth relationship. And this is something that they made a point to highlight in the chapter, was that we can use our validation set to determine hyperparameters such as threshold, as long as the relationship is smooth. If the relationship is not smooth, we can assume that it's going to be overfit to this particular validation set. If the relationship is smooth, as it is in this case, we can assume that it's going to generalize to other validation sets as well. So I'm going to look at my best threshold, where best is strictly numerical. And I'm going to see at what index do I have my maximum accuracy, and what is the threshold at that index. So if I take a look at that, it's 4679. So then I'm going to run this model again. Or sorry, I'm not going to run the training, but I'm just going to assign the metrics again. And I'm going to give it the best threshold. And then I'm going to validate. What's up? What did it not like? Oh, sorry, I shouldn't call accuracy multi. I'm just setting the metrics. Okay, so the partial function receives a function and then whatever parameter I want to set. Okay, there we go. Okay, so this will go through the validation set, recalculate the accuracy with a threshold of 0.4679. And I'm probably not going to get this 96. Yeah, I've got 95% this time. Okay, so maybe you will get something higher. Maybe you use a different learning rate. Maybe you run it for more epochs. Maybe you have a different threshold with the combination of learning rate and epochs, and maybe you get something higher. All right, but still very cool that, in a matter of half an hour, I was able to run the model numerous times, change hyperparameters, test for different hyperparameters and their impact on accuracy, and then establish at least one data point or one milestone for this particular multi-label classification problem. Okay, so the next thing that we're going to look at is the final piece in the chapter reading, which is a regression model. A fundamentally different type of problem than classification. So for classification, we were trying to categorize a picture with a certain, one or more labels, or no labels, as we'll see in an example. For regression, we're trying to quantify something about the input value. So whatever we get as our independent variable, in this case it's an image, the output variable is some quantity on some continuous range. So basically it's just a number or a float, for example. They give this very, I think, powerful statement, which I look forward to unpacking over the next 5-6 chapters, which is a model is defined by its independent and dependent variables along with its loss function. That means that there's really a far wider array of models than just a simple domain-based split. So this domain-based split is the distinction between computer vision and natural language processing, and so on. So what they're trying to say is that you can use different blocks, transform blocks, for different input and output variable types with the same model, change the loss function, and achieve a model that's maybe built on image recognition, but then used for image regression, which is what we're going to do here. So the data that we use in this example, we're going to get from the URLs object, which is the head pose data. I'm going to take a look at the files inside the path, and I'll see that here's head pose with their subject 22. Here's an object file for subject 17, object file for subject 22, images for subject 1, and so on and so forth. If I take a look at one of those folders, I can see that I have a JPEG file, which is a RGB image for some particular video frame, and I have a bunch of JPEGs, and then here I have a pose.txt file. So that the frame underscore frame number has both a underscore RGB.jpg and a underscore pose.txt file. The JPEG file has the image, and the TXT file has the coordinate data. So we first define an image to pose function, which takes an image. In this case, I'd say image path. And what it's going to return is a path to that underscore pose.txt. So I'm going to take that string x, which is the file name of the JPEG, and I'm going to take all but the last 7 characters, and then I'm going to add pose.txt. So if you see here, we have 1, 2, 3, 4, 5, 6, 7. So those 7 characters are going to get removed. The underscore before RGB is going to stay. It's going to get replaced with pose.txt. I'm going to grab the image files with the get image files built-in helper function, which takes a path and then recursively reads through it to collect a list of image file names or image file paths. I'm going to take a look at one of those file paths for the image, and then I'm going to take a look at the file path which is created when I pass that image path to the image to pose helper function. So here we see the original frame 00421 has an rgb.jpg, and I convert it to a pose.txt. So this is going to be helpful for my data block, because my x independent variable is going to be the image, and that's going to be the getX helper function or the getX parameter. For the getY parameter, I'm going to use this image to pose function. So we're going to look at our data, and I'm going to do so by creating an image object with whatever this first file is. And I'm going to take a look at its shape first. So I'll see it has 480 pixels by 640 pixels. I can take a look at a thumbnail, which is smaller, a third of the size. So you can see the image here. And then this is taken straight from the distributors of the dataset. This is how they recommend, or this is how they provide instructions for extracting the coordinates for the center of the subject's head in the frame for each image. So I don't really know the details of this, just kind of copying and pasting based on what they go through in the book. Let's take a look at the coordinates of the first file. So I'm going to pass my getCenter function the first file path, and here it shows me that at 334 pixels horizontally, 270 pixels vertically is the center of my image. So now we have everything we need to specify the data block so that fastai can access the data set, get its items for the inputs, the images, get the outputs, the coordinates, and then also split the data for validation. For the data block, the blocks I'm going to give for X and Y variables are the image block. So it's going to take the file path, it's going to create a pill image object, and then I'm going to give it a point block, which is going to take my center data, center of head coordinate data, and convert that to two floats that will be the output of the model. I'm going to get items with the getImageFiles function. I'm going to get my dependent variable with the getCenter function. I'm going to split my data into training and validation sets by using the subject 13's head poses as the validation set. And then they've also applied some transformations to each of the batches. So it's going to convert the size. It's going to make it a bit smaller. So instead of 480 by 640, it's going to use half of the size. And then it's going to normalize using ImageNet stats. Not very familiar with this. Haven't looked into it too much, but yeah, can't speak too much about that right now. So I'm going to go ahead and run this cell, and then create my data loaders. Giving it my file path to the images. And then I want to see one of the batches. I want to see 9 images, and I want to see some small figures. Okay, cool. So I have a batch created. It shows the coordinates, and it shows the images. So if you look up here, when I had this image just from the file path, it didn't show me the center coordinate, but because I'm using this point block, it's taking that center coordinate data and it's actually showing me the point on the image, which is really cool. I'm going to take a look at my tensors from one of the batches. I'm going to see that each tensor has 64 images or 64 point coordinates. There's 3 channels for RGB and then the pixel size. There's one tuple with 2 coordinates, x coordinate and y coordinate. I'm going to take a look at one of those pairs, and you can see that it's a tensor point. So it's not a tuple, it's actually a tensor point, and it has 2 values, 2 float values there. I'm going to create my learner, which is still going to be a CNN learner. Give it my data loaders. I'm going to use ResNet 18. And here I'm going to say that my Y range, so the output range, is going to be between -1 and +1. So when fastai, and I think it's PyTorch, uses a point block, the Y range, the output range for X and Y coordinates is from -1 to +1. I'm going to just copy and paste this plot function code. This is straight from one of the fastai libraries. And I'm going to use that plot function to show this sigmoid range that we're going to use for a point output. So the sigmoid range is essentially a transformation it's a stretch and a shift on my plot for a sigmoid. So if I give it an input x, I'm also going to give it a low and a high for the range. So my low is going to be -1, my high is going to be +1. And I want to return sigmoid of x, but I'm going to multiply it by the difference, or like the amplitude, between my high and low. And then I'm going to shift it by the low. So in our case, low is -1, high is +1. So I'm multiplying it by 2. So the sigmoid usually goes 0 to 1. I multiply that by 2, so it goes 0 to 2. And then I'm going to add the low value for of my range, which is -1. So I'm going to shift it down 1 unit, so my sigmoid goes from -1 to +1. And then I'm going to use the plot function that I defined in the cell above. I'm going to give it a partial for sigmoid range, and I'm going to specify my low and high values per parameters, and then give it a minimum and maximum value for its domain. So if we see here, -1 to +1, and there's a smooth transition between the two. So here's my continuous function, and I'm going to be picking values off of this, or the model will be picking values off of this for its prediction. So this is the regression output. It's also using sigmoid, which is really versatile. The loss function is going to, learn.loss. So it's going to use the mean squared error loss. So we're measuring how close we are to the actual value, actual distance between the expected coordinates and our predicted coordinates. So here we're going to use our learning finder again. And this might deviate from the notes I have, or the full template filled template that I have provided in the description below. So the steepest point is at 5 e neg, what is that, 2? So if this is e neg 2, 1, 2, 3, 4, 5, so it's somewhere here. The suggested one is much farther back. So in my previous example, I used 2 e neg 2, which is right here. So I'm going to go ahead and just use that. And then I'm going to fit one cycle for 5 epochs and give it my learning rate. So the fit one cycle training regime was inspired and discovered, or I guess researched and invented by Leslie N. Smith, who's a researcher, a U.S. Navy researcher. I think he's in Baltimore, Maryland. So he has an archive paper about this fit one cycle, this one cycle method. I think he calls it one cycle with the number 1. And he essentially starts at a very low learning rate. And as he goes through the training, the learning rate increases to some maximum. It comes back down and then tapers off. And he found that this sort of deviation, in his paper, he actually did multiple cycles. So it was almost like this triangular function going from some minimum to maximum, again, back down to minimum, and repeating a few times. And he found that he was able to get higher accuracy with fewer data points in a quicker amount of time. So I'll link that archive paper in the description as well. Definitely check it out. It's a very digestible, approachable research paper. You can implement what he's doing and really understand how he arrives to some of his conclusions. After 5 epochs, my mean squared error loss on the validation set is about 3 10,000ths. So if I take 1 minus the square root of that, I'm gonna get my accuracy, which is about 98%. Okay, so the conclusion I'm just going to put in here straight from the text, where they say that in problems that are at first glance completely different, so through this notebook we saw single label classification for a 2-digit data set, a 37 breed data set, multi-label classification for the Pascal data set with 20 different possible labels, and regression with this BUI, I think that's how it's pronounced, data set with head poses. We end up using the same model with just different number of outputs. So in some cases we have one output, it's a 0 or 1, representing a 7 or a 3. We have 37 outputs from index 0 to 36, 20 outputs, index 0 to 19. That was for the Pascal dataset. And then in this case, we have 2 outputs in the form of one tensor point. The loss function is the one thing that changes, which is why it's important to double check that you are using the right loss function for your problem. They go on to say, make sure you think hard about your loss function and remember that you most probably want the following: cross entropy loss for single label classification, BCE, so binary cross entropy, with logits loss for multi-label classification. So that's using that negative logarithm for the final loss calculation, or mean squared error loss for regression. So again, we used the same architecture, the same type of model, very similar data blocks, but obviously very, very different loss functions. So that completes my review of Chapter 6. Next, I'm going to work on the second point in the further research section of this chapter, where um, they give us the following prompt. Retrain the Bear classifier using multi-label classification. See if you can make it work effectively with images that don't contain any bears, including showing that information in the web application. Try an image with 2 kinds of bears. Check whether the accuracy on the single label dataset is impacted using multi-label classification. So the Bear classifier that they're referring to is a single label classifier that we trained in chapter 2 of the textbook. And the web application that they're talking about is the web application we deployed in chapter 2 as well. So I'll take a look at that at the end. All right, so I've got my setup done, upgrading fastai, checking that it's 2.3, mounting my Google Drive. Next, I'm going to recreate what we did in chapter 2. So I'm going to create a data block. That's always my first step. I'm going to give it an image block for the input variable, category block for the output variable, which is a single label. I'm going to use the getImageFiles function for the getItems parameter. GetImageFiles will receive a file path. It'll go through it and extract the file paths for any image files. I'm going to use random splitter, so it'll take 20% of the full data set and assign it as the validation, and it won't use it for training. I'll use the parent label of the folder as the output label, and the parent label is used here because all of my images are in folders with the type of bear as the name of the folder. So I have grizzly, black, and teddy as folders, and then each one of them has its images. I'm going to resize each one to 224 by 224 pixels, and I'm going to use at minimum 50% of the image in the crop. So I'm going to run that. Once I have that established, here's my bears data block. I'm going to call the data loaders method, pass it the file path, and then for the validation data loader, I'm going to ask it to show me a batch. And oh, my path is not defined. So let's do that here. So for my path, I have the root folder, which is content/G drive. That goes into my drive. That goes into my folder that I've created for this course. I have images, and then I have bears. So here I can see that I have a teddy bear here, grizzly, teddy, and grizzly. That looks good. I'm going to view my training batch, just 4 images from one of the batches. So I have a grizzly bear, a black bear. Not sure if that's just a brown furred black bear. Looks like a black bear and a teddy bear. So what they recommend is to use a very rough first training. So there's no setting of hyperparameters in this one. I'm simply constructing my CNN learner by passing my data loaders, an architecture, and an error rate. And then I'm going to fine tune it for 4 epochs. So this first um, model that I've trained, um, I so the purpose of this training is taking this model, seeing where it misclassified images, and then taking a look at those um, losses. And for the images that had the highest losses, it usually is because the image is just a bad image. So maybe it's a grizzly bear, but it's maybe a drawing or some kind of illustration or graphic that's not a photograph, or sometimes it's just completely unrelated to the label. So because we are using Google searches for these images and just downloading a bunch of URLs, um, there is going to be some random images in there. So Teddy might give a picture of someone whose first name is Teddy. And so that's not going to be classified correctly. So I've already cleaned this data set manually as I went through different iterations. So I'm not going to run the following cells. I've saved them from the first time I ran them so I can show the output and talk through the process of cleaning the data set. So the first thing they recommend is always to plot this confusion matrix so we can see what the actual labels were and how well the model predicted a black, grizzly, or teddy bear. So you can see here that there were 4 grizzly bears that were predicted as black bears. There was 1 black bear predicted as a grizzly. There was 1 grizzly predicted as a teddy bear, and the rest of them were correct. So if I look at the top losses, so show me the images that had the highest loss, I'm going to see the ones that were mislabeled, and that's why they were misclassified. So here, this was predicted as a teddy bear, even though it was a grizzly bear, but it wasn't a picture of the grizzly bear, so I went and deleted that image. Here, this was predicted as a black bear, but it was actually a grizzly bear. Um, that, I think there's nothing we can really do about it. I'm guessing maybe the snout looks long and maybe the skin or the fur um, is dark because there's shadows, so maybe it saw it as a black bear. I think this is incorrectly labeled in the original image as a black bear, so it should be labeled as a grizzly bear. This polar bear image should be removed. And this one here, we might just have to stick with this. I'm not sure if this is a grizzly or a black bear. Maybe it's like a younger grizzly bear, so the shoulder hump is not present. But I don't know enough about the difference between bears, so I'm just going to keep that. Or, I could also just delete it because I'm not sure what it represents. So what I'm going to use, or what I used the first time, was the image classifier cleaner, which is a set of widgets that can be used to relabel or delete any images from the training or validation set from any of your classes of images. So this first dropdown lets you select the class, grizzly, black, or teddy. The second dropdown lets you choose your training or validation set. And then this dropdown here, either you can keep it, so it won't change anything, you can delete it, or you can select another class and you can relabel that image. The way that it works is that if the ones that you select delete, it stores the index of that in delete, it finds the file name, and it unlinks it from our path variable or path object. The ones that we want to change, it stores the index and the new category, it meaning the cleaner object. And then it uses the shutil library to move it from its current file path to the new file path under the new category folder. So yeah, this is Grizzly training data. If I selected black for this dropdown, this category would be the string black. And so under my bears path, under my black bears path, it would then move this file. So really interesting way, an interesting approach to make your life easier, especially if you have a large data set. You can quickly identify images that are not correct, move them around, and then continue with your training. Okay, so I'm going to now do a second training because I cleaned the data set. So I have all the images that I wanted to remove. I removed them. Any images that I wanted to move, I moved them to the separate folders. So now I'm going to create a new data loaders object. Okay. All right. So nothing really changed here. It's the same path, same data loaders as before. But if you were walking through this top down, once you did the initial training and you cleaned the data, you would want to reset your data loaders to get your new images loaded in to training and validation data sets and data loaders. I'm going to also take a look at my training data. Okay, so here's a teddy bear and then 3 black bears. I'm going to now create my learner. And then call the lrfind method. So this is going to go through and train the data, calculate the loss, while increasing the learning rate for every batch. All right, so it started at all right, so it started at 10 to the negative 7 as the learning rate. Increase it all the way to 1.0, and the loss fluctuated a bit, and then it stabilized, and then it just pretty smoothly started to decrease. So I want to pick a learning rate that's in this region because it's a smooth decrease of loss. It's not going to get caught up into any one of these kind of more unstable regions. So in my example, when I did it before, I used 1 times 10 to the negative 3. So I'm just going to go ahead and use that same. Before I do that, I want to make sure that I have cross entropy as the loss function because this is a single label classification. And once that's confirmed, I'm going to go ahead and train this using the fit one cycle method for 5 epochs at my learning rate of 1 times 10 to the negative 3, which is somewhere around here. So I was able to obtain results better than what I did in my first run, so I had about a 4% error rate. This one is down to about 1%. I'm going to take a look at my confusion matrix next. All right, so I had 4 grizzly bears incorrectly classified before. Now I only have 1. Um, I removed that polar bear, so now none of my teddies are incorrectly classified. So now I'm going to take a look at my results. So I see the ground truth label is on the top and the prediction is on the bottom. So all of these were correctly classified. Okay, I'm going to export this model for now because later on, if I want to load it back in and use it for prediction, I can do that. So I just call the export method. I give it a file name, which is my file path, followed by whatever file name I want to give, and a .pkl extension, because it's a pickle file. All right, cool. So now we're going to implement what we learned in Chapter 6, which is multi-label classification. And I'm going to review the 3 major differences between training a multi-label model versus a single label model. And we're going to do it on the same data set. So first of all, the dependent variable is the decoded string for our single label model. So if it's a black bear and the string is black, that's what the output is of the model. For a multi-label model, the output of the model is a one-hot encoded list. So if I have, in this case, I have 3 classes, so I'm going to get a tensor that's 3 elements, with 3 elements. It's going to have a 0 for predictions that did not fall above the threshold, and it's going to have 1 for predictions where it fell above, the activation was above the threshold. For the loss function, my single label uses cross entropy, which uses softmax. And what I've understood the main point of that to be is that softmax sums to 1.0 across the entire tensor of activations. So if I have 3 different activations in this case, the sum of those activations will be 1.0. When I use binary cross entropy for multi-label, it has a different approach. It uses sigmoid with a threshold. So the entire summation of the activations does not equal 1.0. But in each individual activation is going to be between 0 and 1. And if it's larger than the threshold, then it's going to be considered a prediction. If it's not larger, so if it's smaller, then it's not going to be considered a prediction. And that maps well. This true-false tensor that I get, this Boolean tensor with true where it's above the threshold and false where it's not, that's going to be compared with the one-hot encoded list. So true maps to 1.0, false maps to 0, and that's how the accuracy is calculated. The last difference is between the getY function values in my data block. So for single label, I'm just using my parent label because it accepts a string and then it predicts a string as the dependent variable. For the multi-label, fastai expects a list of labels. So because I just have a single label, I'm just going to wrap my parent label output inside of a list and then pass that to the data block. So I'm going to start with that getY function. It's going to receive a file path. It's going to pass that file path to the parent label function, which will return a string with the name of the parent folder. I'm going to wrap that inside of a list and then return that list. And I'm going to see if I can just copy paste this here and change what I need. So I'm still using a data block with an image block, but now I have a multi-category block. I'm still going to use get image files to get the file paths that feed into the image block to transform them into a pill image. Except my getY is now user-defined up here. And so that's what I'm going to pass to the getY parameter. I'm still splitting 20% randomly, and then I'm still resizing the images. So I'm going to create my new data loaders. Same file path, because my images are the same. And let's take a look. Here's a teddy bear, black bear, grizzly bear. This looks incorrect, but I'm not sure. This is probably just a bad picture. It has a lot of background images that are well defined. Here's a teddy bear, here's a grizzly bear. I'm going to make my learner with the same data loaders and architecture, but I'm going to use a different metric. I'm going to use my multi-label accuracy, and I'm going to give it a threshold, let's say of 0.5 to start. And then I'm going to find the learning rate at which I'm going to train the model. Okay, so in the example, I used 2 times 10 to the negative 2. That looks fine to use again. I'm going to check my loss function, make sure it's PCE with logits loss. So here, it's taking that negative log of the sigmoid value. I'm going to set the new learning rate, fit for 1 cycle, 5 epochs, and the learning rate here. I don't think I mentioned this before, but fit 1 cycle is a training regime that was created by Dr. Leslie Smith, who's a U.S. naval researcher out of Baltimore, Maryland. And I will link the research paper, the archive paper below in the description. I highly recommend you read through it. It's very approachable and understandable, and it reduces the amount of images that you have to use, as well as the amount of epochs you have to train. in order to get a good accuracy. Okay, so I get about 93% accuracy. Now, I could also vary the threshold and see if I can bump that up higher. I'm not going to do that right now because I have a number of things left that I want to cover. Okay, so here's the ground truth at the top, the prediction at the bottom. Here, this grizzly bear was the ground truth. The model did not make a prediction because it didn't know what that was. Probably too much else going on with these flowers and the grass and all that. Okay, so I'm going to export that model, and it's going to be my multi-label one. All right, now we get into the final piece where I'm going to infer what the label is of my input image for the single label classifier and a multi-label classifier. The path of images that I have, it's going to be under this images folder. I have a test folder. So let's do this. I'm going to load that path and then see what images I have. So I have this grizzly test 1. I have a car, computer, a donkey, real AI. This was an image from Zachary Mueller's walk with fast AI example. Same thing with the Persian cat. Let's see, so I have grizzly teddy. So that's a combination of a grizzly bear and a teddy bear in one image. Grizzly black. I have a grizzly teddy black, and then I should have a teddy black somewhere as well. Okay, so my first image I'm going to test is with this grizzly test 1. I'm going to load my learners. And then I'm going to predict using my single learner. And it predicts a grizzly bear with 99% confidence. And my multi-learner also predicts grizzly bear. You can see the output here of whether or not the threshold of and the default threshold is 0.5. I can change that if I wanted to, but here it's a very confident prediction. So here the image is correctly classified by both. Okay, so I'm going to now test both models. Okay, so maybe it was black and grizzly. All right, so here's an image I just slapped together with a grizzly bear and a black bear. Let's see what the single learner predicts. The single learner predicts a black bear with a pretty high confidence. The multi-label also predicts a black bear. So the multi-label classifier doesn't understand that there's also a grizzly bear here. Next, I'm going to do a image with a grizzly and a teddy. So again, just a image I put together. Let's try single label. So the single label gets distracted by the teddy bear. The multi-label also gets distracted by the teddy bear. And it's not even close. So that's interesting. Okay, I'm going to try a black bear and a teddy bear now. Okay, so here's the image, same teddy bear, same black bear as before. The single learner, again, predicts this only as teddy. So does the multi-class. So my multi-learner is not recognizing. I'm not sure if it's just the one I trained today. I had trained one earlier, which I'll show you when we get to the web app portion, and it had a better ability to predict two bears. But the one that I've built today, not a good result. Okay, I'm gonna try now. I don't need this path. I'm gonna try images without bears. So I'm gonna try this computer.jpg. And single learn infer. Okay, the single learner identifies it as a teddy bear. The multi-class model predicts it as a black bear, maybe because of this value here. Now, one thing that you'll see here is that the summation of these three for the single classifier is 1.0. So if these two values are small, it essentially forces the third value to be very large. On the other hand, my multi-label classifier over here doesn't have that same requirement. So it does not sum, it's not using softmax, so it does not sum all of the activations to 1.0. Each one is within the range of 0 to 1, but they don't add up to 1. So here, even though both of these are very small values for the activation, this black bear activation is not large, or it's not as large as the teddy bear one here. So if I had a higher threshold, let's say if I had 0.9, so let me see if I can try that here. So I'm going to say the loss function, I'm going to use BCE with logits loss flat with a threshold of 0.9. And you'll see that none of these values cleared the threshold for 0.9. So it actually resulted in no classification, which is good, which is exactly what we want, because this is not an image of any one of our trained classes. Okay, so if you're trying this, hopefully you have better luck with your multi-label classifier. I certainly did when I tried that before, which we're going to take a look at now. So in Chapter 2, they walk through the process of hosting a web application built inside of Jupyter Notebook through GitHub for free using mybinder.org. So here's what we need in order for this to happen. I have my Bear Classifier notebook. So this is what we're going to open up here. So it has the following code, and I'm just going to walk through it here. So I define my getY function, which the model needs, because it doesn't use the built-in function, or it doesn't use anything that's already defined elsewhere. I actually have to user define that. It imports my libraries, and then I just uploaded to GitHub, to the repo, my multi-label Bear Classifier pickle file. Okay, so if you look back here in bear_voila, it's going to have that pickle file. This was actually the one that I trained before that works better. So at least my web app has a working classifier. Whatever I did today was not effective. I'm going to create a button upload. So in IPy widgets, there's a file upload button that gives a little upload button that you can click, which looks like this. I'm going to have a output where I'm going to display the image that gets uploaded, and then I'm going to have a label that prints out the string that I want to show the user as a message to show them what their prediction is and what their class is. So on click, upload is an event handler basically that I'm going to pass to my upload button. So my upload button is going to observe any changes. Once changes happen, it's going to call on-click upload. And as soon as someone clicks that upload file, let me just do it here. So if I click this upload file and I select an image and I choose for upload, and then of course it dramatically does nothing. So maybe I have to reload this. It'll show this string waiting for classification underneath the image. It's then going to create a pill image object using the data from the file that was uploaded. It'll clear the output, so if you do multiple images, it'll clear the previous image. Then it'll display the image you uploaded. It loaded my learner, my model, so it's going to predict on that image and get the prediction, the indexes of the prediction, or true false in this case for multi-label, and then the probabilities or the activations associated with it. And then this label value I'm going to set to the string where it shows what the prediction is and then what the probabilities are. This probs variable is a tensor with probabilities like this one here. I'm going to index it with this true-false tensor that you see here, and then just convert that to a list and print it out. And then I'm finally, just for the UI of my widgets, I'm going to throw them all into a VBox. So it's just going to stack them in a single column. So let me see if I can get this to work. I'm going to click on my launch binder link. So I'm going to click on my upload link or button, select a file, choose for upload, and here we go. So this model works better. It predicted this as a black as well as a grizzly bear with pretty high probabilities for both. Let me try some of the other ones. So here's my grizzly and black. This one, I think this model didn't infer correctly either. Yeah, so maybe there's something about this image that it doesn't like. So this one, it predicted black. Here's one with all three. It doesn't understand either one, so it doesn't pass the threshold. So that's interesting. I've never seen something come out blank with probability, so I'm actually not sure 100% why that's the case. Let's try the grizzly and a teddy. Cool, it classified that. And then let's do our teddy and black. Awesome, so it did that as well. Now this one, I think it did not, or I think it did classify the computer. No, it didn't. It did not classify the computer as one of the three classes. And then let's just try one more. Let's try a car. And interestingly, it finds that as a grizzly bear. So yeah, this is a free simple way to host your model on Binder and have it so other people can use it. It's not, you know, um, good for any kind of production that you're doing, but as a student, this is really rewarding. You can actually share this with people, and it's for free, I think, which is really the key point. Um, you can also definitely um, follow the directions in chapter 2. They have some deployment training guides on the website course.fast.ai. They walk you through how to host um, and deploy on GCP, Google Cloud Platform. I recommend that you do that at least once, once or twice, as many times as you need to understand what's going on, because it's relevant to or closer to what a real deployment would look like. Um, but honestly, I think as a student and even as a practitioner, if you're just sharing this to someone else as a prototype, it's a really clean, neat way to use Jupyter Notebook and get this up and running in a few minutes. Okay, so that finishes chapter 6. I'm going to now go back and continue through chapter 7, and probably next week I will post a video of a walkthrough of chapter 7 as well as any further research that they have us do. Thank you.